This semester, students at the University of Maryland are designing and deploying their own LiDAR sensors using Raspberry Pi and OpenCV, specifically an E&ME 435 remote sensing. Each student captures 3D data of a campus landmark, contributing to the growing and collaborative point cloud map of the entire campus. My target of interest, a lamp mounted on a brick wall near Somerset Hall. The reason I chose it, I saw it flickering one evening, and then it went out. Thought that would make a great scam. The LiDAR sensor I built used a horizontal line laser in conjunction with a Raspberry Pi camera to perform a triangulation-based distance measurement. As the laser projects a line across the scene, the camera captures the distortion of the line across surfaces, which is then processed to extract depth information and generate a 3D point cloud. This setup is grounded in the principles of the LiDAR equation, which relates received power to range, surface reflectivity, and system parameters. While my sensor doesn't use time of flight, the core idea still applies. The accuracy and quality of my 3D measurements depend on the reflectivity of the lamp surface, specifically the glass, ambient light, interference, and the geometry of the laser camera setup. To calibrate the sensor, I first performed a horizontal line test by projecting the laser across a flat wall and verifying that the captured laser line appeared level and undistorted in the camera frame. This ensured that the laser and camera were properly aligned and that the system could detect deviations caused by surface depth. Next, I conducted a distance validation test. I captured one image of the laser line at a fixed distance, then moved the system back 6 inches and captured another. By comparing the shift in the laser line's position across the images, I verified that the system could distinguish depth changes accurately and consistently, and graph these changes using a code developed in class. The next stage was deployment, which was frustrating. From an environmental standpoint, I faced several challenges. The area was surrounded by bright lights that washed out the laser line, so I covered the reachable light sources with towels and bags. The target itself was about 8 feet off the ground, which I solved by stacking my LiDAR rig on a table, then an ottoman, and then a wide box, and then taping the entire tower together. The lamp also had an angled glass panel that caused the laser to reflect and refract back onto itself, corrupting the depth data. I fixed this by cutting white paper triangles and taping them over the glass panels to create flat matte surfaces. On the hardware side, I didn't have a mobile hotspot, so I bought an Ethernet dongle and a long cord from Micro Center, which worked. But then the data came back skewed and ultimately unusable, especially because I then had found out that it reflects off the glass when shined. When I went back to try again, the dongle stopped working altogether. Just tried. Desperate, I borrowed my roommate's phone and used his hotspot for 3 hours. He's a saint. Thank you, Evan. After a third round of recalibration, I finally collected clean, usable data. Of note, I was only able to collect 3 sides of the lamp: the front, middle height, the pathway, lowest angle, and the back, highest angle. While this didn't significantly impact the quality of the point cloud itself, which still looks solid, it did affect the mesh reconstruction. The missing side limited surface continuity, and because each view was captured from a different height, I had to apply extra translation and rotation during post-processing to align the data properly, which I'll talk about shortly. And yes, I did stack books to change the angle. I didn't have a tripod, so I taped down the back legs and stacked books underneath the front leg to change the angle and measured it with my phone. This worked. No questions. To plot the data, I first transferred all the photos from my Raspberry Pi to my computer using a flash drive and organized them into separate folders by angle. In my data generation script, I use a path wildcard to load each set of images. Each image was then processed through an HSV filter, which I custom tuned for each picture to account for differences in materials and lighting conditions during scanning. I stored the HSV bounds in an array and dynamically called them for each image set to ensure accurate filtering. I then applied custom parameters to crop out unnecessary regions. These were determined by visualizing the data in OpenCV and adjusting the view to isolate only the useful points. This approach significantly reduced noise and cleaned up the data before writing into a text file and saving it into the folder as test results. Then we did the entire thing over again for the second angle and the third angle from the sidewalk and from the back. After generating the test results.txt file, I loaded it into Cloud Compare for visualization and further cleanup. Using the snip tool, I manually removed any remaining noise that slipped to the HSV filtering. To mesh the scans together, I imported all three angle sets at once, then used rotation and translation tools to align them accurately in 3D space. Once the point clouds were fully combined, I applied a height-based color and gradient to enhance the visual structure of the scan. Finally, I increased the point size to make the feature more readable and give the model a more cohesive, finished look. Finally, to create my mesh, I go to Edit, Normals, and Compute. This computes my normals. I select OK, and then I go to Plugins and Poisson Recon. After the pop-up menu, I make sure Output Density as FF is selected and create OK. Now, this is our final mesh.